If I said, what is solubility? What would you tell me?
I would say that's a good question.
That's a what?
I'd say that's a good question.
Sorry, what? That's pretty much. But when you say that's pretty much it. Except when you say the solubility, it's the maximum amount. Okay. So when we're talking about solubility, we're talking about the maximum amount of a solute that can dissolve in a certain amount of solvent at a certain temperature. You always have to give the temperature. Why do you have to give the temperature? Yes, because most things, as you increase the temperature, become more soluble. Not everything. Okay. So it's the amount needed to saturate a solution. All right. It's given in moles per liter. All right. But I've also seen it in grams per liter, grams per 100 mils. Like it's all different things. We're going to tend to stick to moles per liter. Okay. Because moles we can measure. Sorry, when high solubility substances are formed as products in a single or double placement reaction, the maximum quantity of the solute that can be dissolved in the solvent is rarely reached. So if it's really soluble, you can keep dumping stuff in, right? Some things you'll never reach. We'll talk about that in a sec here. It's difficult to reach the saturation point, all right? So we, as the solute dissolves, we write the AQ. That just represents it being dissolved. Okay? So if you see, like in our reaction when we did sodium chloride, when you write those things, that means it is dissolved in this case, water, the AQ. Okay? So if you see an equation like that with the ions in AQ, you have dissolved it in water. We don't write the water because the AQ represents the water. What's that? Then you'd have to define that, what it is. Sorry? Well, if you're going to dissolve it in acetone or paint thinner, you'd have to state. You wouldn't write AQ though. You would just say, you'd probably say the liquid, like, or whatever it is, if it's a liquid. NaCl plus methanol, MEO, CH3OH. You'd put it into the equation. Do you know what I mean? You would literally just go like this. Like that. We're going to learn how to write net ionic equations in a sec. Okay, so, but you'd have to state what it is in some sort of pre-statement, I guess. Okay. All right. Some substances have very low solubility. All right, and if you remember back to, I think it was stoichiometry, and you look in your data booklet here. We had this table that tells you if you have low solubility. If it's low solubility, what do we call that? What does it mean? It means there's a solid forming. What do we call the solid that forms? It's a precipitate. They settle at the bottom, and we call these a precipitate. Okay? All right, so there's some solubility trends / rules. I don't know, like rules, because there always seems to be exceptions to rules, but solids usually, highlight the word usually, have higher solubility in water at higher temperatures. So if you increase the temperature, you increase the solubility or the ability to dissolve more. Gases, I think we've talked about this, always have a higher solubility in water with lower temperatures. So the lower the temperature of the water, the better you're able to dissolve a gas in it. Gases always have a higher solubility in water that is at high pressure. Because the pressure will keep the gas in solution. It's like when you open a can of pop, what do you hear? You hear that? That's the gases expanding and released from the liquid. Okay, because you release the pressure. The can of pop is under pressure. As soon as you open it, you release that pressure, so some of the gas comes out. And if you've shaken it, right, it has a whole bunch of energy in there. It's fine as long as the pressure is on it, but as soon as you open it and release that pressure, it bubbles over because all of the gases have expanded instantly, and that's what the foaming over of the pop is. Okay. Some liquids, oils, do not dissolve in water at all, but they form a separate layer. We call these immiscible. Hello. Yep. All right. So we say they are immiscible. They're not mixable, I guess you could say. So if two things are immiscible or immiscible, you cannot mix them, no matter what you do. If you shake them, if you shake oil and water, it looks like it's mixed, but it's mostly just bubbles, and you've added enough energy. Once it settles, once it calms down, settles out, they'll go right back to the two separate layers. Some things you can just mix in any proportion. You keep adding water or keep adding this, in this case, they're using methanol. You can just keep adding it, and it will never reach a saturation point. All right? This is said to be, what do you think it's called? Miscible. First one is immiscible. This one is miscible, which means they're mixable. And just as a side note, not everything is 1-to-1 ratio when you add them and mix them together. Like if you had 10 mils of water and you add 10 mils of water, what's the volume of the new substance? 20 mils. If you have 10 mils of water and you add 10 mils of methanol, the volume is not 20 mils. All right? Because depending on the sizes, the molecules can get in and they form tighter little bonds. All right? So it's not always a 1-to-1 ratio unless it's the same liquid being added together. All right. What are we doing here? Saturated solutions. So if you have salt dissolved in water and you just leave it in an open glass or beaker or whatever on the table, what's going to happen to the water? You have a beaker of water. You just leave it on an open table. What happens? Some of it will evaporate. As it evaporates, because solubility is dependent on volume, all right, what will happen is you'll have, say this was salt, NaCl, will start to form a precipitate on the bottom, all right, because you're changing the concentration, right? You're removing the water and you're changing the concentration. So you can call that crystallization. You've probably seen it in honey when the sugar crystals crystallize out in honey, all right? If you just heat up that solution, they'll go back in, okay? We already talked about this. If you have the carbonated beverage, when you open it, you're releasing the dissolved gases because you're changing the pressure. This one, you've probably seen this. If you have a cold glass of water, you let it sit, you get little bubbles forming. All right? Remember, this is cold water. So gases dissolve better in the cold water. As it comes up to room temperature, the gases don't dissolve as well, so they start to come out of solution. That's what the bubbles are that are forming. Okay. Okay, predicting solubility. Our data table. So in the data table, it's defining soluble as more than 0.1 moles of solute dissolved in 1 liter of solution. That's the definition in the data table, and it's at 25 degrees. You have to give the temperature. Okay, so if we look at the data table, there it is right there. Oh, I can't see. Soluble is defined to be greater than 0.1 moles per liter at 25 degrees. Okay, if you increase the temperature, the definition of soluble would go up. All right, you can dissolve more. Soluble in chemical reactions. Okay, this is where we're going to start to predict whether we get a precipitate forming or not. We've already done a bit of this. All right. If you have two soluble ionic solutions, boom, with molarities greater than 0.1 and they're mixed together, there's 3 different things that can happen. 1, all the combinations of cation and anions are soluble, so no precipitate. Are you okay if I put PPT for precipitate? I'll put it in brackets, and then I want to write it again. Or one combination of the cation and anion have low solubility, and you get 1 precipitate forming. But sometimes, so this is like, remember at Halloween when I did the lead and I added it to the water, the lead nitrate solution, and it turned bright yellow? That's a precipitate forming. That's the second one. You get 1 cation and 1 anion, form a precipitate and fall out of solution. But sometimes you can get both. You can have both combinations and you'll get 2 different precipitates forming. And it's all based on the table. So So what we're going to do now is we're going to learn to write what's called a net ionic equation. All right, when you mix ions together. All right. So I will ask you to do this on the final exam and on the group quest that we're doing in 2 days. So we are mixing lead 2 nitrate and potassium iodide. So the first thing you got to figure out is what is going to happen here. So the word equation, what's going to switch? If you mix 2 ionic compounds, what switches? You're just pointing. The lead and the metals will switch, right? Okay, so they're going to switch. So you're going to get potassium nitrate and lead 2 iodide. Okay. What type of reaction is this? It's a double replacement reaction, right? You okay there, Mary? Okay. So there's the word equation. Now we're going to write the balanced equation for this. So lead 2 nitrate. What's the formula for lead 2 nitrate? It's in your data booklet. NO3 2. That's lead nitrate plus potassium iodide. Ki. So we're switching. We're forming potassium nitrate. What's the formula for potassium nitrate? Plus what? PBI2, because it's lead 2. Okay. You have to put the states. So lead nitrate, if we look, and potassium iodide, if we look on our data table, anything with a potassium ion or an alkali metal is always soluble. So if it's soluble and we're in water, all right, we write AQ. PbNO3. There's NO3. Nitrate, NO3, is soluble with everything. So if it's with lead, here on this side, it's AQ as well. All right. So if you're with NO3 or an alkali metal, you're always soluble. So what do I put with potassium nitrate? What's the state that I'm going to put here, the subscript? It has to be AQ. Okay, lead iodide, PbI2. Where is it? Oh, it's up. There it is. Sorry. There's the iodine. With everything, it's soluble except for silver, lead 2, and copper 1. Okay? So it's low solubility. That means we're going to put a solid there. That's our precipitate. This is pretty much the exact reaction I did with you guys. Yeah, I know. That was the next thing I was going to do. So we're still not done because every chemical reaction has to be balanced. How do I balance this? There's 2 nitrates there. There's only 1 there. 2. But now I have 2 potassium. I need 2 potassium. Is it balanced now? It is, because we have 2 iodines, 1 lead, 1 lead. So we're good. Okay, balanced. So that's the balanced formula equation. We have the word equation with the balanced formula equation where you put all the states. Then we have the full ionic. Nobody likes the full ionic because what you have to do is you have to write everything in its ion form. So it gets really big. So instead of writing PbNO3 we write, Pb plus 2. So you have to think of what's happening in the beaker. All right, I'm throwing lead, nitrate, and potassium iodide. The lead is dissolved in water, so it gets Pb ions, lead ions, plus we get NO3 minus ions. You have to balance it. We have 2 of them. Plus we have potassium, and we have 2 of those, so 2K plus aqueous plus 2I minus aqueous. And then you have to do the same to the other side, except for the precipitate. The precipitate does not dissolve. It's a solid sitting there, so it stays as PbI2. The KNO3 is going to be rewritten as 2K plus aqueous plus 2NO3 minus aqueous. But the lead 2 is a solid and does not break up. All right, so that's what's happening in the beaker. You have these ions all broken up. You throw them together. The lead and the iodine come together to form a precipitate, and they bond like that in an ionic bond. But the potassium and the nitrate, they're dissolving, so they're just floating around as free ions. All right, and they'll come together and then they'll come apart. They'll come together and they'll come apart. And then in grade 12, we would call that an equilibrium, but we're not going to worry about that right now. That's the net ionic. The net ionic, everything's written in ionic form as its ions, separate ions, except for the precipitate. Okay? Then you write, or sorry, that's the full ionic. Now we're going to write the net ionic. Okay? The net ionic is sort of like math. Okay? I know that probably scares the bleep out of everybody. But what's on one, they cancel if you want to think of it that way. This potassium will cancel that. This iodine, well, the iodines don't cancel. The nitrate and the nitrate cancel. Okay? And it's not that you're canceling. You're only writing, when you do the net ionic, the two ions that form the precipitate. So in this case, this is our precipitate, so it's just lead 2 plus 2 iodine. So we go Pb2 plus aqueous, 2 I minus aqueous forms PbI2 solid. That's the net ionic. Just what forms the solid. People like to use the acronym we be fine. If you want to memorize that, that's fine. We is the word equation. What's going on? B is the balanced equation. So the word equation, the balanced equation. I guess FINE. FI for the full ionic equation, and then NE for the net ionic equation. Or you just know what to write. Okay? Word equation, balanced formula equation, full ionic, net ionic. Nobody likes the full ionic. I understand that. Okay? The net, you just write what forms the precipitate. Is that okay? Thumbs up. You know what? We just finished the unit. No. There's the we be fine. Write the full net formula. Do all that stuff for this page, please. You're gonna have to predict the precipitates as well.
So it's tomorrow.
Review.